This series focuses on data structures and algorithms content, and particularly in this recording I will talk the second part 2 of the selection sort algorithm subseries, how to code a function implementing selection sort algorithm. I have this code to begin with. In the main function I have an array called data containing the values 8, 6, 18, 6, 3, 12, 9, 36, 21, 15, and I have a print function which receives the array and the size of the array, and it displays the element in the same row uh, by executing the iterations of this loop. First, I want to make sure that I don't have any issue with this code before I actually I start discussing the selection sort algorithm. Let me compile it, do compilation and linking. This is just a warning. I will not be worried about that because the reason it is warning is it has not been used. The variable is not been used. So let me do execution. I have no problem with this code. Let me go back to the code. The warning was because it is complaining that I have not used this size. This is actually supposed to be used in this place. And another complaint was this array has not been used. So let me call this print function with this data and size, then try to do the compilation one more time. So we have this array displayed 18, 6, 3, 12, 9, 36, 21, 15. Going back to the code. So if I want to reorder this elements or rearrange these elements in increasing order or in ascending order, then I will need to have a logic. So I want to put that logic in a function called, let's say, selection sort. This is the function, and I would call that function after I actually initially display the data to see the original version of the data. I want to pass data and size, and then after that I want to print same data again to see what actually happened during the sorting process. So this function should receive the array, but in this case no, like unlike in the print case, this print function is not only accessing data and displaying, so we have a constant here on not modifiable. Here we cannot have that because we will be actually maybe swapping the elements. Swapping is the one of the thing that is carried out during sorting, so we cannot have with this constant. If the logic tries to do that swapping operation, then compiler will actually obviously complain. So we don't want to have constant here. Now if I want to do the sorting, the way selection sort does is actually finds searches in the, actually the algorithm runs in several passes. Pass 1, 2, 3, and so on. If you have watched my previous recording on the concept, on the explanation of sort, then you should be familiar with what this pass means. In the beginning, in the first pass, what happens is the program will find the minimum value from among all the elements of the array. In this case, this is minimum value. Actually, it will find the minimum value index of the minimum value. In this case, index of 18 is 0, index of 6 is 1, and index of 3 is 2. It will find the value 2, and once it is found, it will actually swap, use that index to swap with the first element. So 3 will go to the place of 18, 18 will go into the place of 3. So let us see how that happens here. So first you need to find minimum value, and after that you do sorting. These are the two main tasks in the pass one. So to find a minimum value, I would obviously check all the values, maybe minimum value index. I want to use a loop. Let me have the loop iteration variable j equals to 0, j less than size j plus plus. Here inside the for loop, what I would do is I want to actually have some, I want to compare data j with some presumed or some pre-assumed minimum value. And if this value, to be more specific, you want to see whether this is smaller, this j is smaller than some pre-assumed minimum value. So if I want to use a if statement here, I would put something like this. If it is smaller, then you want to change the update or index of this minimum value to j. For example, if you assume that one item of this, one element of this array is minimum, then if you found another element to be smaller than that element, then obviously the index of that minimum should be updated to this j value. So we need to actually have a variable to actually carry the index of this pre-assumed minimum value. Let me call it this min index, and we can initialize. Initially, in the beginning, we can assume that this min index in pass 1, particularly in pass 1, we can assume that this is a minimum value. That means the index of the minimum value is 0. So we can set it to 0, and you compare this with data. If it's smaller, then you update j equals to, sorry, min index equals to this should give a minimum index. Let us see what happens here. If I want to display index, and also the value. So I want to see this thing here. So let me quickly check how will this the code that I have just added will behave. Now index 2, value 3, that means 0 1 2. This was the value is 3 and the index of 3 is 2. And back to the code. Now it is working okay, but I need to come back and fix some things here. Let me remove the things that is not necessary and comment this out. Now what we do is, if min is not the first index, right? So if, for example, in case if first element happens to be 1, in that case that logic will determine the minimum value index equals to 0, right? So in that case we don't want to swap, because essentially what we will be doing is, if I have minimum index, then I will be swapping this minimum value with the first value. But if the minimum value is itself in the first position, then we don't need to do swapping. We can just skip the swapping process. So for that purpose, we want to check whether it is minimum index is not the first index. So the way of doing that is, if min index not equals to 0, because the first index the first value that this variable carried in the beginning was 0, and if there is another minimum value which is smaller than this first value, then this logic will definitely update this value, otherwise this logic will not update. So the same 0 value will be there, and if this is the it contains 0 value, this will be false, and this swapping operation would be skipped. So for the swapping we need to have a variable, let me call this temp, and copy equals to data that we want to swap, and copy the min index, the minimum value to the first element, data 0, index, and then again copy it back equals to temp. So this is the swapping process. Right, so this will find the minimum value, this will perform the swapping. At the end of the first pass, that data will be displayed here. And let's see what happens when we actually compile and see the output. So you can see it was initial minimum value was assumed. The 18 was assumed initial minimum value, and the minimum value was searched in this among these elements, and it was found. This was found to be minimum value, and then it was swapped with 18 and 6. 3. 3 went in the place of 18. 18 went in the place of 3. There is no other additional change in the other elements. Only change was the swapping of the first and third elements here. So this is the first pass, and in the second pass we want to actually lock. In the second pass we will lock 3. We don't want the logic or algorithm or loop to toss this value. This will be locked, fixed, and it will work only on these values, and it will assume that this first is a minimum and sorts among other elements whether to see whether there is some value which is smaller than the first value. If smaller is found, it is swapped, otherwise it is just skipped in second pass. So in second pass we can do something. I can just copy this everything I have here, and in the second pass we want to lock. We don't want to toss this 0 index element, so we start with 1. The first minimum we assume is the second element, and we actually before that I actually want to talk about this loop. So here we have started from 0, and in the first iteration of this for loop, this expression will be basically like this. Min index is 0, and this j is also 0. You are essentially evaluating this expression, and you know that this is pointless to evaluate this expression, because obviously if you compare the same value is less than, it's going to be false, right? This is known, so this is not going to be true. So so this is pointless having this comparison. So for that purpose we actually start from j equals to 1, not 0. Or if you want to generalize it, you can do it like this. Maybe I'll do that afterwards, right? So this is, we start from 1 and go up to this size minus 1. So here if we have 1 and then we start from 2, and we are not working with the index 0, so we have to work with index 1 in this case. So this is the second pass. So if I want to see what happened in the first pass and what happened in the second pass, I want to print data here at this point, and the result after the second pass will be displayed by this print function itself. So let me see what happens now. So in the first pass 18 and 3 were actually swapped, nothing else changed. In the second pass 3 was locked, and 6 was assumed minimum value, and there was nothing else, no other value smaller than 6, so the swapping step was just skipped. So the array is essentially the same after the second pass here. And in the third pass we will lock 3 and 6, and 18 is assumed minimum, and it will search for the minimum or the minimum value, and 9 will be found, and 9 and 18 should be swapped in the third pass. So let me remove these things because I will not be needing this. So this is finding minimum value, and this is the swapping. Let me just write. These are the computational components. So pass 1, in pass 2, and in pass 3 we follow the same process. It's kind of a pattern. If you can pick the pattern, then you can generalize this in iteration. So in pass 3 we don't want to toss the first and second element, so we start with 2, and here it is going to be 3, and we compare with this element, third element. This is after pass 2. Now you can see after first pass we have this outcome, after the second pass we have this outcome, and for the third pass these two elements were fixed, they were locked, and this 18 and 9 are actually swapped. Okay. Now this is not the way I have to put this passes is not a good efficient way of programming, because same logic is actually repeating again and again, and only the difference is that this index is changing from 0 to 1 to 2, and it will continue. So if it is happening, then we can have a loop. Let me call it let me have a loop with iteration in index I equals to 0, I less than size I plus plus, and put everything inside it. Right, so now at this point in the first pass this min index should get 0, in the second pass it will be 1, so it is actually linked to this variable I, so we set it to I, and here j starts from one variable more than the value that min index is getting. In this case 1, if min index of 1 it would be 2, if min index is 2 it would be 3. So we have I plus 1, and here we compare with I, because the first index in this case, in the first pass it is going to be 0, we compare with 0. In the second pass I will get value 1, so we compare with 1, like in this case. In the third pass, I will get value 2, so we will be comparing with 2, and we actually do swapping with I. So this is the code here, and we don't need this code because we have put everything in the loop now. So just remove this part, and we have a nice compact and clean code here. And one thing I want to clarify, just make sure that you understand this expression and this size. We have I plus 1 because we want to lock the, I mean, we don't want to compare with the first element. That is kind of a redundant thing to do. We want to skip unnecessary comparison here. Here, if we start from I equals to 0, and if we go up to size, what will happen is size up to I equals to size minus 1. At the end, what will happen is, I mean, in the beginning, we are assuming this is a minimum value. This 18 is minimum value, and in the end, we'll assume that this will minimum value, and you search for the minimum value afterwards, which is not necessary. If you have only one value, you can assume that as a minimum value. So if you go up to this point, then you can search whether the next value is smaller than this value. If smaller, then you do swapping, otherwise just skip it. And at this point, we don't need to search for the minimum value. The value that you have is itself only one value, which we can assume as a minimum value. So therefore, for that reason, we don't need to go beyond size minus 2. So we go up to size minus 1. Right. So this is the code we have. Let me run it and see the output. So we have in the first pass only 18 and 3 and 18 are swapped, nothing else. In the second part, 6 was locked, 6 was minimum value, so it was not swapped. There was no swapping. Swapping step was skipped. In the third pass, these two elements were locked, and 9 was found minimum. It was swapped with 18 and 9 swapped. And in the next pass, these 3 were locked, and 12 was found to be smallest, and there was no swapping. In the next pass, we have these elements locked, and previously it was 18, and 15 was found, and it was swapped. 15 and 18 were swapped. In the next pass, you have these 4 items were locked, 5 locked, and 36 was initial minimum value, and 18 was found smaller, so they are swapped. And after that, everything is in sorted order. So this is the final outcome of the function we have over here. And one additional two additional comment I want to make here is that if you want to, this is in this case we have sorted in the ascending order. If you want to sort in descending order, then only change you can make here is very convenient change is instead of comparing for smaller, you can compare for larger, greaterness. So if you compare for greaterness, and what will happen is instead of putting the smallest element in the first position, it will start putting the largest element in the first position, and then second largest in the second position. So that way it will naturally be sorted in descending order. So let me show you in the output. So in this case, this 18 was assumed minimum in the beginning, and the largest value was found out, 36. It is swapped with 18, and then 36 was locked, and after that here 6 was assumed the largest value, and the largest value was found to be 21. It is 6 is swapped with 21, and 36, 21 locked. The 3 was assumed the smallest largest value, and it was the largest value was source. 18 was found, and the 3 and 18 swapped, 18 and 3. And after that, 36, 21, 18 locked. 12 was 12 initial value, 15 the largest value, so the 12 and 15 swapped. And we have this elements locked, 9 and largest value 12, so 9 and 12 swapped. 12 and 3 was initial value, largest value happened to be 9, so 3 and 9 swapped, and these are locked. And 6 happened to be larger, so there is no swapping here. So it is ordered in descending order. That is one way of doing that. And another way, a little bit kind of complicated way, would be maybe you want to put the element here. You are actually selecting the smallest value and putting in the first position, but if you select this value and start putting in the last position, second last, then it will be naturally sorted in descending order. And the way of doing that is maybe you want to have this loop in the reverse order. Maybe start from size -1 and you go up to, let's say, greater than 0, and you I minus minus, right? So start decreasing, and after that you may want to iterate from search. This is searching for minimum value, so you may start from 0 because I is on the right side, so start from 0, maybe I minus less than I think that should be okay. And once you find and you do swapping it with I. So let me quickly check. I think should be okay. And so let me try. I believe this works, but let me try. Just I'm not 100% sure. So let me go to the terminal. So looks like it is working. So in the first, the largest element was selected and placed in the first position. It was, I think, swapped with. No, the smallest element was actually swapped with the rightmost element. So smallest element went here, and then second smallest element assumed 21, and but 6 was found to be smallest, so 21 and 6 swapped. And then after that 9 was itself the smallest element, and then 36 was assumed the smallest, and 12 was found smallest, so it is 36 and 12 swapped here. And these were locked, and these were locked, 36 and 15, and 15 locked, and 36, 18 was found swapped, so 18 is locked, and 21, 36. So it is in the descending order. So this is all I have to talk about on this topic. Thank you for watching the video.